delay we are about to measure. Yeah, I can quickly play the animation. Yeah, the animation shows what I just described about the frames, and yeah, you can see how cars are stacked up based on the color of light. Okay, let's go to the next slide. So result, another result. On the left is a single simulated hour. The top plot is Q length over time. There's the sawtooth. I just um sawtooth kind of pattern in the graph in the plot. It grows during red, the white band, and drains during green, the shaded band. And the bottom plot is the input output diagram and cumulative arrivals versus departures, where the horizontal gap between the curves is each car's delay and the vertical gap is the number queued. Um, Both performance measures in one picture. The top right is conversions. A single hour is just one random sample. So I ran 400 independent replications and tracked the running average delay. You can see it settle and stabilize around 17.6 seconds. Uh, with the confidence band shrinking like 1 over root n, so the number is reliable, not a fluke. Yep. And the bottom line histogram is the interesting one. So delay distribution is bimodal. There's a big spike near zero. Uh, Cars that arrives on green and sail through, and a spread of longer delays for cars caught on red. A single average of 17 seconds hide that completely, which is exactly why simulation is worth doing. Okay, let's go next slide. Load sensitivity and control strategy. These two findings are the engineering core of the project. So on the left is the sensitive sweep, average delay, and maximum Q as I raise demand. Um, Notice how flat it stays at first, and then and how violently it turns up right around 674 vehicles per hour. Um, that's the capacity. So the point where x equals 1. Below it, it delays. It the delay is gentle. Above it, delay and Q explode, and the intersection simply can't clear the cars. That ni is the single most important um, number for sizing an intersection, and the fact that it's so abrupt is a real warning against running intersections near capacity. On the right is fixed time versus um, actuated contour on identical demand. Um, the fixed time plan average about 4.4 seconds of delay. The actuated controller, which gaps out unused screen and hands it to whoever has cars waiting, cut that to 7.1 seconds. That's a 51% reduction, purely from a smarter strategy with no new infrastructure. And the box plot shows it's consistent across all 20 runs. It's not log. Signal timing optimization. The last result turns out the simulator into a design tool. Here I fix the demand and swap the cycle length, rerunning the full Monte Carlo simulation for every candidate, looking for the cycle that minimizes delay, and you get the classic U shape, which reassuringly is exactly the Webster trade-off from traffic engineering. If the cycle is too short, you waste too much time on startup and lose time, and the intersection saturates. That's the left side shooting up. Um, if it's too long, driver just sit through long red, the red side climbing. Um, the sweet spot here is an interior optimal around a 28-second cycle, or roughly 9 seconds of delay. The key point is that the simulator isn't just evaluating one design, it's searching for the best one. To wrap up on conclusion, the big picture takeaway is that a handful of simple Monte Carlo primitives, a uniform generator, a linear congressional generator, invert transform sampling, a discrete event loop, and replication, compose into a genuinely faithful model of a messy real stochastic system. Concretely, the baseline intersection averages about 70 seconds of delay with, with a bimodal distribution. The stability limit sits right at 674 vehicles per hour with a strikingly abrupt knee. Actuated control saves about 51% of delay, and optimization lands on a 28-second cycle, recovering the Webster result. Uh, the other lesson I would stress is that validating the model against both the data and non-theory is what makes the output trustworthy. For future work, I would replace the point Q with a spatial car following model to capture spillback, extend to a full four-way with turn movement, coordinate several intersections into green wave, and optimize the actuated controller's own parameters. Yep, that's the project. A data-driven Monte Carlo simulation that both visualizes traffic flow and produces real engineering conclusion about capacity and signal timing. Uh, Thank you for listening, and yep, thank you.